All right, welcome back, everybody. I feel impelled to share with you about the power of practice and how practice leads to progress and repetition's the mother of mastery. And there's all kinds of examples from my life and that illustrate that and prove that. And the reason I want to share that with you is because if you want to own this material, you got to work it. You got to use it. You got to apply it. You got to think about it. And you know, there's several times I became really good at stuff and I didn't mean to. I just kept doing it. It wasn't like I set out to become good at something. Like at one point in my life, I started going to a rock climbing gym with a buddy, and we'd just go every Thursday night. And then after a couple of years, we were climbing really hard routes. And that was just because we just kept doing it every week. And another time in my life, I got into what my boss calls power swimming. And power swimming and is masters swimming, which is like team swimming for old people being you're out of university. And I never swam competitively before, but I joined a team. And when I started out, I was in the slow lane, but then I just kept going. And after a couple of years, I was in the fast lane. I was one of the fastest swimmers. And so if you just keep doing something, you get better at it. And that's like hard to know when you're young because there's can be a desire when you're young to like really get to that end point. But the main point is if you want to own this material or if you want to own anything, if you want to own anything in terms of knowledge or skill, you just have to keep doing that thing. And then over time, you're going to get good at it. And so that might be something that's common knowledge. When you hear it, you might be like, oh, yeah, of course, no duh. And but it's not always common practice. It's not always common practice to know how to apply that in your life and just to keep doing it. And we could get weary. There's this song, Ella Fitzgerald, that comes to mind. Ella Fitzgerald. Young women, they do get weary. I think it is. I think it's black coffee, maybe. And this is more of a chat GPT question. Google's just going to go, I don't know. What is the song? What is the song? Is the song with the lyrics? It might be like the guy who did sitting on the young women. They do get weary, or something like that, or something like that. Is it Black Coffee by Ella Fitzgerald? We'll see. Song you're thinking of is Try a Little Tenderness. Jimmy Campbell, Reg Conley, Harry Woods, and line young girls, they do get weary wearing that same old dress. Yeah, so, you could get weary. You could get weary doing the same thing day after day. Like, I'm a little weary of statistics. Weary. I'm a little weary of statistics. How do we say that one? Just, we're just like seeing it all right now. Weary.
Weary.
We're a little weary. I'm a little weary. Feeling or showing tiredness, especially as a result of excessive exertion. Exertion. We've been doing statistics in 9 weeks, which means I've been doing statistics just like every day. A lot of statistics. I'm a little weary of statistics, but we're in chapter 13. We're getting to the end of 13, and we're just going. We got one more thing after this chapter, and that's regression, and that's 14, and then we're done. But anyhow, there's part of me that just wanted to be really cursory about block design. But then this morning I sat down for an hour, I don't know, maybe 2 hours, and I put this together, which is going to illustrate why we need block design and how block design is useful. So we're going to go through randomized block design here, and we might just do a cursory touch on factorial experiment. So these are the last two things, module 13. I really like this description from the textbook about randomized block design. So I just put this in here so we could read it. And I'm going to crop this here because all we have to look at is that part there. And we don't need all this stuff down at the bottom. And when we make it landscape, it gets bigger because you have more room to stretch out. There we go. Let's make it like that. Kapow. And now we could do this. And then we could do this. And there we go. Just you and me hanging out doing some statistics. All right. Randomized block design. Thus far, we have considered the completely randomized experimental design. Recall that to test for a difference among treatment means, my heritage is on my mom's side of the family Southern. It's Southern on my mom's side of the family. Recall that to test for a difference among treatment means, we computed an F value by using the ratio of Mr. Mouse. A problem can arise whenever differences due to extraneous factors, ones not considered in the experiment, cause the mouse part, the MSE, and the mean square treatments, right? Like we could go and we could come, oh, I didn't put my little thing back up here. So let me grab this one and grab those two things and put them up at the top. Our terminology pages, I'm going to Control C them from over there and then just put them right here. But recall that we have the mean square of treatments, which is between treatments, TR here, treatments. I don't know, that's how I connect it. And then within treatments is mean square of error. And I think of standard error, which is like standard deviation, which is like looking at like, you know, how much are these points away from the mean altogether? How much do they vary? But it's the square root of variance. So a problem can arise whenever the differences due to extraneous factors cause the MSE term ratio to become large. So if this term down here becomes large, then our F statistic is going to be small. And what can happen is we could calculate it with ANOVA the regular way. And so here's the regular ANOVA, and here's our test statistic with the regular ANOVA, and we say do not reject. But when we calculate it doing the block design, whereas what block design exists for is block design exists to try to eliminate any noise or extraneous factors which can make this become extra large. Right? Block design exists to eliminate that, and when you do that, this is not unnecessarily large, which means if it's smaller, this value is going to be bigger. Because when we have division, let's just review what I'm talking about. Okay, so I'm going to do a little note here, and I'm going to make this like, I just want this to be like 10, should be good. When we have division, if we have, let's say, 100 divided by 2, that is equal to 50, right? But if we have 100 divided by 25, that is equal to 4. And so I'm just actually going to flip these around because that's the way we're talking about it here. And boom, boom, boom. All right. So when we have 100 divided by 25, if we have an unusually large value in the denominator, then that's going to make our quotient, which is the result of division. It's going to make our quotient, our F, it's going to make it small. If we have a big value down here like 25, the quotient, the result of the calculation of division, is going to be small. But if we have a smaller value down here in the denominator, then the result of our division, the quotient, is going to be large, right? And so what we're saying is a problem can arise whenever differences due to extraneous factors cause the MSE term in the ratio to become large. Well, what is MSE? MSE is mean square of error, aka within treatment's estimate of variance. So when we have data, like right here, if that data is varying a lot within the treatments, if there's a lot of variance in here, then that MSE can become large, okay? So where did it go? Where are you? That MSE can become large. It's the mean square error within treatment's estimate of variance, right? So it's our MSE. And that's like the standard error. That's the error within a single treatment as opposed to between treatments. And so we have a lot of variance here. And if you even look at how MSE is calculated, it's NJ minus 1 times variance. And that's the variance, and then you add all those up. That's the variance for each treatment, for each set of data. The variance here, the variance here, the variance here. So the main takeaway is if you have a big number here, if you have a lot of variance here, it's going to make your F statistic small, because when you have a big thing in the denominator like 50, right? Or sorry, a big thing in the denominator like 25, you're going to get a result from that division which is smaller. And if it's smaller, you might say, hey, do not reject. The population means are all the same. But really, if you took that variance out of the data, and there's a way to do that, you'd say, no, reject that. And we're going to see that. And so, like, I guess philosophically right here, I just pause and say, do you want to take the variance out of the data? And the answer to that question might be beyond our pay grade. Like, we don't have to understand how the BMW is engineered to drive the BMW. We don't have to understand how these formulas are engineered to use these formulas. But what we do need to know is that people who have devoted a lot of time and become really good at something, statistics, got their doctorates and whatnot. Not that they don't make errors, because we've all seen that they do throughout this textbook. But people have devoted a lot of time, have figured all this out, and so we don't have to know how to engineer the entire BMW. We just have to know how to use the engineering. Likewise, we don't have to know how to create all the formulas. We just have to know how to use all the formulas. And so, taking that on face value, that this MSE can become large if there's a lot of variance in our data here. And that's a little bit too big for me. I kind of like being able just to kind of take it all in at once. There we go. Ba-dum-bum-bum. All right, so that's the purpose of having a block design, and we've learned all that just in these first two sentences. In such cases, you could pause and reread them. In such cases, the f-value equation can become small, right? When this denominator is too large, the f-value becomes smaller, signaling no difference among treatment means when in fact such a difference exists. In this section, we present an experimental design known as randomized block design. I'm going to talk in a southern accent because I'm feeling it. Its purpose is to control some of the extraneous sources of variation by removing such variation from the MSE term. So control extraneous sources of variation. This design tends to provide a better estimate of the true error variance and leads to a more powerful hypothesis test in terms of the ability to detect differences among treatment means. To illustrate, let us consider a stress study for air traffic controllers. So they were wondering, like, hey, if they have workstation A or workstation B or workstation C, which causes least stress? So they have a controller, and then they have each controller do system A, system B, and system C. But they randomly assign the order in which the controllers do the systems. So you're not, every time with each controller giving them system C last, by which time they might be tired or they might have gotten used to switching systems. And so you're mixing it all up, and that's where the randomized factor comes in. And anyhow, you're looking to see which one causes the least amount of stress. So that's the idea. And then what I did to create this is I created this spreadsheet here. So let's go take a look at it. And so here I have block design. I'm going to put that at the front, so that's what pops up. And here's all the data. And so here's the data, right? This is our initial data. 15, 15, 18, and so here's 15, 15, 18, and we get all that data, and then we could start to do some calculations, and we could do our regular ANOVA. And so to do our regular ANOVA, so with all this data here, right, to do our regular ANOVA, and then this is the block stuff over here, but to do our regular ANOVA, I totaled up all of the data there, then I found the means for each of these. So the means of all of that is 13.5, the mean of all of that is 13. The mean of all of this is 15.5. And if you just want to pause and look at the formulas, you can see those right there. To see these, I'd have to stretch everything out. I don't want to do that. And then we have our mean of means. And so the mean of means is going to be all three of these means added up, divided by 3, which is that formula. And you can see that formula right here. Or it's going to be all this data added up, divided by 18, because there's 6 3 times, which is 6 times 3 is 18. And so here's the same result. And then to get the variance, I need to find the difference between each point and the mean. So the difference between this point and the mean, right? And then I need to square that. And so here's the formula for that. The difference between the point and the mean times the difference between that point and the mean. And then I did that for every point against each mean, and I got all of this data here, okay? And then I summed all that data up, because that's the next thing you need to do for your variance. And let me just go get that formula. Hold on. All right, there's the formula for variance, right? So the first thing you do is you find the difference between each point and the mean, and then you square that, and that's what I did with all this. Boom, 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 boom. And I really just want that formula here on the screen. So I'm going to go here, I'm going to go to Insert, I'm going to go to Image, I'm going to Insert Image Overlay, and I'm going to go get that right here, and I'm going to drag that file just so you can see it. Drag that file here and drop it there. And that file is getting dropped in. It's getting dropped in, and there it is. And then I could click on that, and I could move it over here, and I think that's good enough. All right, so here is the variance. That's how I calculate the variance right there. And so you sum it all up, right? Here you sum it all up. And then once it's all summed up, you have to divide it by n minus 1. So we have n is 6, right? We have 6 elements in our sample. And then minus 1 is 5. And divide this by 5. And you can see that formula right there. And you do that for each of these, and you get these. You do that for each of these things summed up. When you divide it by that, you get that. And then that is our variance, right? So there's our variance. I'm just going to make that bold. And I think I'll just also make it yellow, because that's, I'm not, it's going to be too much yellow. Yeah, I will, because I got totals yellow. It's kind of like, you know, endpoint right there. So there's our variance. And then we take the square root of it just for kicks. That's our standard deviation. And then to get our SSTR for regular ANOVA here, we follow this formula. And so again, I went through all of this. So what is the mean minus the mean of means, right? So the mean minus the mean of means. And then I did that. So the mean for our SSTR, oh yeah, so here we have it 3 times, right? So the mean minus the mean of means, so you can see here's the formula for it, and it's B10, so here's B10. There's my mean, and then my mean of means is B11 right here. And so 13.5 minus 14 is negative 0.5. And then here we have 13 minus 14 is negative 1. And here we have 15.5 minus 14 is 1.5. And you can see the formulas there, so you can see how it's calculated. And then you square each of those, and you can see the formula there, right? So you square each of these here, and you get this, because it's like each of those squared. And then you multiply each of those that have been squared by nj. And so nj is like how many things were in each sample, right? So here's nj is equal to 1 to k, and it's like, you know, j is 1, and j will be 2, and then j will be 3. It should, yeah, that works actually, is 1 to k. So it's the number of treatments that we have, and nj is how many elements are in our sample for each treatment. And so we multiply by nj, so each of these is going to be multiplied by the count of this, which is what that formula, which will be 6. And so that's what that formula here says, times that. 6 times a quarter is going to be 1.5. 6 times 1 is 6, so there you get that. And then you sum all of that up. There it is. You sum it all up, you get this. And then you divide by k minus 1, and k minus 1 is, where's our degrees of freedom? It's right here. K minus 1 is 2. It's 3 minus 1. We have k treatments, k number of treatments. And we get 10.5 for our MSTR. So there's our SSTR, there's our MSTR. And then this is the ANOVA block over here. So continuing down, right, we got our MSTR. Now we need our MSE, because to get our F value, we need Mr. Mouse. And so to get this one here, right, we do nj minus 1 multiplied by the variance. So we needed our variance up here to be able to do our mouse part, our mean square. I want to just say mean square error every time. It's mean square error. It's perfect. That's exactly the right thing to say. There's so much terminology soup in statistics. So to get our mean square error, we have to use our variance, and it's going to be nj minus 1. And so here we have, again, our count, and there's 6, and minus 1 is going to be 5. And then 5 times B21, which is our variance, will be like 5 times 4.3 will be 21.5. 21.5. And that is the variance for the first one, and here's the variance for the next two. So I should also make those guys yellow just so we see them, and bold that. So there's the variance for the next one, which is going to be, and then we sum all those up and we get 49, right? And then once, because 21 plus that's 31, and then that's like 48, and then one more is 49. And then our MSE is going to be to divide that by the total number. So NT is a total number in our all of them. I think of it kind of like this is the population, though it's not, right? But it's NT minus K. So it's a total number of, I'd say, I don't know, observations and everything we did, minus the number of treatments. So it's 18. There's 18 here. 18, that's your NT part. And it's minus K, and there's 3 treatments, 1, 2, 3. So 18 minus 3 is 15. So you then divide this number here, your SSE, that part, by your degrees of freedom, this part. And when you do that, and here you can see the formula, and that formula is this amount right here, 49, divided by 15 degrees of freedom, and that gives us 3.3. All right, well, with that information, we could calculate our F value of 3.21. Our F value is 3.21. And so looking back up at this right here, and let me just make this bigger, boom, and boom, we have 3.21 as our F value. Well, at 0.05 level of significance, 95% confidence, and when we have 2 degrees of freedom in the numerator and 15 degrees of freedom in the denominator, and those degrees of freedom are calculated right here, okay? Degrees of freedom for the mouse part, which is the denominator of our test statistic, and degrees of freedom for the Mr. part, mean square of treatments, right? That's the between. That goes in the numerator. Mr's in the numerator. So these are our numerator degrees of freedom. So we have 2 in the numerator, 15 in the denominator. We have 2 in the numerator, 15 in the denominator. And if we go look at our F table, and so let me just see if I have F table open. I don't. I'm going to close those, and close that, and open that. And we need our F table. So here's our F table. And our F table with 15 degrees of freedom, which is right here, 15 degrees of freedom. And then also, hopefully I got this right. Sometimes I look at the wrong column. That's in the denominator, and 2 in the numerator, which is right here. So we're looking right there, and 0.05 is 3.68. So at 0.05 p-value, our F value is 3.68, and our test, that's the critical value, our test statistic is 3.21, and 3.21 at 15 degrees of freedom in the denominator and 2 in the numerator, 3.21 puts us like between, 3.21 puts us between 0.05 and 0.1. So between 5% and 1%, because 3.21 is between those two figures there. And so that's what I put here. And both of these are on the do not reject side of our test statistic, okay? Whether we use the p-value approach or the critical value approach, which is that one. So that's doing it the normal ANOVA way, analysis of variance, okay? And based upon that, we would say that the population means are equal. But in our data here, okay, there's a lot of variance. There's a lot of variance in between the data samples. And so our MSE got too large. Our MSE got too large right here, which made our F statistic unnaturally small. So this is a good point to pause the video and read, these first 2 paragraphs right here. And so to account for that variance and to not have this be quite so large, to make it smaller, so when it's smaller here, we're going to get a larger F statistic, we're going to use block design. And when we use block design, we're going to get a larger F statistic. We're going to get a larger F statistic because this is going to become smaller. And when you have a smaller in the denominator, it gives you a larger result when you do division, because this smaller thing can go into this bigger thing more times, right? So you're going to get a bigger number. And based on that, our drawing is going to end up like this, and we're actually going to say, oh, you know what? Actually reject at least 2 population means are different. Okay, so we're going to reject the null hypothesis. And so to see those calculations, I do those. Well, those calculations are here in the book, right? So here it shows you have to calculate a bunch of stuff. You have to do your SSE, and we need our SSE. But to get our SSE, we have to calculate an SST. Right, and we did SSTR up here. Maybe they call that the SST. I don't know. Oh, we do an SST. That's the total. Sorry. And then we do an SSTR, and that's this one. And then we do an SSBL for block. And then to get our SSE, it's this formula right there. So it's a lot of math, and they do that math for you. And you could take these formulas here, and you could look at the data. And so here's the data, right? And you could say, okay, how are they making those calculations? And you could figure it out, and you get all these. And that's how those calculations get done. So all that said, our SSTR is 21, and I just got that from right here because I was tired of doing math. And SSTR is 21. And then our MSTR is going to be that divided by the degrees of freedom, and that's also going to be 2 degrees of freedom. Okay, so SSTR divided by that gives us our 2 degrees of freedom, and gives us this value for MSTR. Our SSE is also calculated here, it's 19, and to get our MSE, we take this 19 and we divide it by the degrees of freedom, but we have different degrees of freedom, and this is detailed in the book also. I think I have a picture of it, so here's that, here's the drawing. I don't have a picture of it, but it's detailed in the book also. You've got different degrees of freedom, and it's on the next page up at the top here. And so to get those degrees of freedom, it's this. Okay, so it's k minus 1 times b minus 1. And k is the number of our samples, it's 3. So number of treatments, 1, 2, 3. And then b minus 1 is going to be how many were in each one of those. So that's my understanding of b. I might have that wrong. It has a little notation here. It doesn't tell us what b is. But anyhow, you do that and you get your MSE, and you take your MR and you divide it by your mouse and you get your F value of 5.53. All right, so our F value is 5.53, but here we have different degrees of freedom. So the degrees of freedom now are 10 in the denominator, and there are also still 2 in the numerator. So I'm just going to copy this and bring that over here, right? And we'll copy this one here. That's the same. So so that's you got 2 in the numerator and 10 in the denominator. So if we go back and we look at our F table, we got 2 in the numerator and 10 in the denominator. And I'm just checking to make sure that that's right. And so looking at this here with 2 in the numerator and 10 in the denominator, at 0.05, our critical value becomes 4.10. 4.10 at 0.05. And I just put these all here so that we could see it on the same page, right? And so really these 0.05s would line up, and we're doing, you know, like just different F values based upon the degrees of freedom. And so that's with the block design. We have a numerator, 2 degrees of freedom, and denominator, 10 degrees of freedom. So we're right here, and that's 4.10. And at 5.53 as our test statistic, this is our critical value, the 4.1. And 5.53 of a test statistic, 5.53 is going to be between 5.46 and 7.56. Okay, so it's going to be between 0.025 and 0.01. Okay, so 2.5% to 1%. So both of these, whether we use the p-value approach or the f-value approach, both of these are in the reject area. They're to the right of these critical values, right? And because of that, we reject. And we say, you know what? The population means are not equal. And so the point of that entire exercise was to illustrate for you how if you have variance, right, too much variance in these values here, right, in each of your treatments, if there's too much variance there, you are going to get a large MSE. When you have a large value in the denominator, right, large value in the denominator, it's going to go into the numerator fewer times, right, so it'll be a lower number, so you're going to get a lower one. However, when you take into account that variation and use block design, you're going to get a smaller number in your MSE, right? And that smaller number will go into the numerator more times, so you'll get a bigger number here. And that bigger number, here's the bigger number, once we use block design, you can see block, the pink. That bigger number could lead to a different conclusion. That, ladies and gentlemen, is why block design exists and how you do it. And it's a little bit laborious, but this is what you do in statistics, right? You like think about these numbers, and if you could see, if you master this, like, wow, you're really going to be able to do some cool stuff with numbers and get some good insights to make some good decisions. So I'm just going to fly through these slides here where the book talks about it, and it, I think, talks about it in a confusing way. Let's do that in the next video. See you in the next video.